fingerprints of orbital physics in magnetic RIXS. So I'm going to show some main aspects of the resonant inelastic X-ray spectroscopy, and I will show some experimental results connected with magnetic excitation, and then some sketches of the theoretical descriptions, and in the end I will derive the dispersion relation and intensities for spin waves magnetic excitation in some ferromagnetic systems. So what is RIXS? It's a photon in, photon out spectroscopy where the incoming photon energy is tuned with to a specific atomic absorption edge, where we measure the outgoing photon energy. And so we are mainly interested in the inelastic features of this process. So that is where when some energy, momentum or angular momentum is transferred into the system. And so in this way we can produce in our system some excitations, so like phonons, magnons, orbital or charge transfer excitation, as far as the total charge is concerned. So we can the main process we can summarize in for example for D9 system. So we have this photon in. Then, okay, in the whole picture, we see that the photon in scatters the O from the D shell to the inner P shell. So here, due to the strong spin-orbit coupling, up spin and down spin are mixed, and so the whole propagates, and there's a finite probability to have a spin flip. So the whole scatters back to the D shell, and so in general we can say that the final state is different from the initial state. So we can, as far as spin and angular momentum is not concerned, we can end up in a different shell or in the same orbital but with a spin flipped. So this is the way that we can probe the DD excitation or magnetic excitation. So here I show some experimental data for lanthanum copper oxide. This is RIXS measurements at the L3 edge, the copper L3 edge, compared with the neutron scattering data. So here we can see a description, a theoretical description of this system. So we describe the XY plane by an Heisenberg antiferromagnetic model in 2D, and the green lines are the dispersion relation of the magnetic excitation, while the red line is the scattering intensity in the RIXS process. And okay, and we can see that the theoretical model can describe the dispersion and okay, also the intensity. I'm not showing here. So from a theoretical point of view, the scattering process is described by the Kramers-Heisenberg equation. So in the single ion picture, so I'm considering just a single ion. I'm not considering here the bulk. I can write down the intensities as a function of this scattering amplitudes. So here we have the initial and final states. E is the polarization tensor, and P is the momentum operator that is involved in the selection rules of the possible transitions. intermediate state propagator. So if we consider that the incoming photon energy is tuned to a resonant edge, so an absorption edge, and if the spin-orbit coupling is large enough respect to the core hole lifetime, we can write this propagator in a simple way as a function of the intermediate state eigenstates related to the core hole excited system. So, in principle, to calculate these amplitudes, one has to know the full Hamiltonian of the system. One has to diagonalize the normal state and the intermediate state with the hole in the p-shell. But for 3D9 system, for D9 system in general, for cuprates, this appears to be simple, because actually in the old picture we had just one particle problem. So so the main point is that we don't have to deal with Coulomb interaction between the shells or within the shells. So what we need is how to write the core hole propagator. So if we analyze the intermediate states, we can see that actually due to the spin-orbit coupling, the eigenstates of the Hamiltonian are eigenstates of the total angular momentum. So the state splits into two subspaces with j equal to 1/2 and j equal 3/2. And if we put here these eigenstates, we can obtain a simple formula for a simple equation for the propagator in terms of the spin operators along the three axes, and this transition operator that creates and annihilates the hole between the p shell. So from this we can find a pictorial way to calculate the scattering amplitudes. So here I represent the d states, orbital states, and here the core hole. So these lines connecting the d shell and p shell are actually the matrix element of the momentum operator, and so this line contains the information about the selection rules and about the polarization. And for example, one can calculate the excitation between an orbital, let's say xy minus y square, and just the pure spin flip excitation. So one has to sum over all possible paths that starts from the initial state and then propagates into the core hole and then comes back. So we can see here in a very simple way that if our spin is directed along the z-axis, there's no way to flip the spin, because actually apart from the identity propagation, we have here with this line and with the sz operator, and actually this operator does not flip the spin. But if we consider the spin laying in the xy plane, this operator it's possible to flip the spin along the xy plane with the sz operator. So we can, in this way, we can calculate all kind of dB excitation and spin flip excitation. So if we if we introduce the bulk, one has to for example, one can consider a ferromagnetic order with the same orbital spanning all the whole XY plane. So what is called ferromagnetic ferroorbital order. So one can then demonstrate that this spin flip excitation can propagate, and so we can calculate. Okay, this is the well-known energy dispersion of a ferromagnetic material, and this is the intensities. So due to the fact that a ferromagnet breaks the time reversal symmetry, we can have a decrease for a certain kind of for the elongated orbitals like 3z square minus r square. And here I plot the intensity, the scattering intensity for several kind of circular polarization. So we can see that changing from left to right polarization, it leads to different kinds of intensities. One can do the same for a ferromagnetic alternating orbital order, and here we can see that due to the fact that our system periodicity is changed, a second mode in the dispersion appears, and this is visible as far as the amplitude in the A sublattice and the B sublattice are different. And so here I plot the two branches of the energy dispersion, and in color are the intensities. So and actually this is due to the fact that our unit cell is doubled in length. And so for that we have that the Brownian zone is folded down. So we have that a second mode appears, and this is not actually it's due to the particular orbital order of the system. So thank you for your attention. Actually, this is more than it's more a prediction of a net effect. But anyway, there are some materials that shows this. Okay, maybe the first case it violates the Moore rule, so but it's still possible to have some materials with this order. And there are materials that shows this orbital order. So in principle, one can try to measure this RIXS process. So the next step is also to calculate the same thing for an antiferromagnetic system. So, where there are more experimental data.
There's some very nice explorers from Marco Gioni from the Swiss light source. They study, I don't know if this is studied, there's some magnetic scattering.
For which kind of system?
It's a dumb question. So both RIXS and the usual neutrons can probe spin excitation. I think what the advantage is here is that you're more orbitally sensitive. Is that a fair assessment? That RIXS in general, it's not even about your calculation, but I think the one of the main advantages is you can probe the orbital at the same time as magnetic.
Yeah, actually, even if you are just calculating the the magnetic response and the magnetic amplitudes, this amplitudes depends strongly on the orbital degrees of freedom.
The structure factor.
Yeah, the structure.
Yes.
I don't know about a lot about neutron scattering. So
But okay. But so, I mean, I'm trying to compare the two techniques and just see what the advantages are of one with respect to the other. That's, I mean, you know, I'm looking at it sort of from the outside. I don't know much about RIXS. Yeah. So that's what I wanted you to comment on.
Yeah, okay. For example, there's no counterpart for decreasing. So,
Yeah.
And yeah, because, and I think that maybe with one can prove one can do a measure, and then afterwards with RIXS one can discriminate between different kind of orbital or magnetic orders. So
I mean, comment that that's a technique almost. You can use much smaller crystals for the RIXS than for neutron.
Okay. I know. This is theory talking here. What the advantages of experimental calculus? By the way, you can do it on a smaller sample. Yes. Okay.
There is actually a conceptual advantage. Is that with RIXS you can look at the DB excitations. So even just simply looking at the electronic structure, it's one of the few techniques that gives access to the anti-electronic states. I mean, we can discuss why people don't look at the anti-states. It's hard. So optical spectroscopy, in principle, could do it for these compounds. All these emission compounds, the anti-states are these D nature things, and the field states are also D mostly. So exciting from these to these is not easy.
So the Fermi function doesn't enter. That's what you were saying, right?
Well, it's one of the few techniques.
In the same way.
It's being a second order technique, it's one of the few techniques that gives access to this transition. So this is something that Newton's going to do.
Okay, more questions? If not, I think all the speakers.